All right, hello and welcome to week 45 of Chill Kernel Hacking for Fun. Let me update my top text to correct what we're doing today. We are doing copy on write in user space today. Cow in user space. We are proceeding slowly and steadily through lab 4 of the MIT course. And last week, on week 43, actually, is where we successfully reached the end of exercise 11. And we got user space page fault handling working. I'm just going to reproduce this over here so we can run this fault alloc. That's fault alloc. Okay, we can run. This is fault. Oh yeah, this is fault alloc, right? And when we run the fault alloc program, we can see this text being printed, and the most important part is right here. The string was faulted in a dead beef, cafe buffa, fault cafe C1000. This string was faulted in a cafe buffa, which is exactly what we see here, which is great news. So that means our user space page fault handling is fully working. I'm just going to do a quick test 0 in the chat just to see if the chat is working. Hello to anybody joining. Yes. Quickly open up Git just to see what's going on. We'll quickly review the Git history. So I was doing all these exercises and double fault handler. This was actually not really relevant. I actually have squashed everything into the appropriate commits. Yeah, I think this was the most critical, actually. This was writing all the assembly, and it's actually been a few weeks for me, so I would need to go back and remember, but I did a few optimizations to this after I ended the last stream. I think all I'm going to do is just briefly show my tweet about this, which explains I think I won't go, I can't do it right now, okay. I tweeted about this here. Yeah, I tweeted about this here, and I optimized a few things, I believe, to optimize some stack operations. And I just want to make sure that is still in what we're doing. Yes, that is what we're doing. So yeah. Okay, so just to recap, because I will find it helpful to do that. What I changed is I used to actually consume additional stack space when doing this return back to the main user code that was running before the page fault happened. So in the code we're looking at the code that executes after the user space page fault handler executes. So that finishes execution, and then we have a bunch of code that needs to return back to the original stream of execution. And originally in the process of doing this, I actually used I guess I can't zoom in very well. I used a bunch of extra stack space, actually. You can see I did a push of EBX on the stack and a bunch of stuff. What I have opted to actually do to optimize this, to rather not use more additional stack space, was I actually started to mutate the trap frame argument that was passed in. I realized that rather than pushing, like I needed to cache the computation of the ESP-4 because after a certain point, I can't do math anymore. And so I need to save that computation in a variable. And I was previously choosing to do this by pushing another variable onto the stack. What I actually realized I could do is mutate this ESP variable and compute that -4 and then write it back into this slot in memory. So that's what we're seeing here. Yo, what's up, David? Are you still hacking on x86 kernel? Actually, no. And actually, I have not been hacking on x86 for a pretty long time. I am hacking on this thing called JOS, which is part of this MIT course, actually. I'll link the course here. It's actually different from x86. And it's much better for, doing OS hacking for learning, in my opinion. What's up, me? Hey. So briefly just explaining that. So I guess I'm just have my comments here. So the idea was to, we need to compute the ESP-4 thing, but that's an EBX. And that gets written into memory. You can see the other stream if you want to learn more about this code. Then my optimization was I actually mutate the structure. I write it back into this slot. That's why it says ESP-4. Then I move the stack pointer all the way up to UTF regs. I skip over these two things and I do the pop AL, which pops all the registers off of this stack into the actual registers. Then I add ESP+4 to skip over the EIP. And then we are perfectly in position to do the final steps here. So we do a pop F to pop the E flags off. We do a pop L ESP to pop the ESP-4 off the stack into ESP. And then finally, we return. So I know that all was really intense and technical, and honestly, there's no way anyone could even understand this unless you've been following along very, very closely with what I'm doing. So don't feel bad if that made zero sense to you. It was really deep specifics of this exercise. You can go back and watch week 43 if you want to understand that better. So that was just a bit of context, and now it's time to move on to implement copy on write fork. Before I do that, I am just going to see if I can just delete a few things here. This was me, remnants of me debugging the user space page fault handling. Don't need this anymore, and I don't know, I'll keep this around. It's not very clean to keep around this debugging stuff, but it might come in handy. So yes, so now we have a nice clean state and we can keep going. Okay, I'm going to just make a new space for myself over here. This is 12:08:45. And at we're at 9:54, finish recap. Okay. Let's take a look at what we're going to do today. This will probably involve me reading through a bit of this. You now have kernel facilities to implement copy on write fork entirely in user space. We have provided a skeleton for your fork in libfork.c. Like dumb fork, fork should create a child environment, a new environment, then scan through the parent environment's address space and set up corresponding page mappings in the child. The key difference is that while dumb fork copies pages, fork will initially only copy page mappings. Fork will copy each page only when one of the environments tries to write to it. The basic control flow for fork is as follows. The parent installs page fault as the C-level page fault handler. The parent calls exofork to create a blank child environment. For each writable or copy on write page in its address space, or copy on write for each. Okay, in its address space below, the parent calls a dupe page, which should map the page copy on write into the address space of the child. And then I'm also going to make sure my break timer is set up. Okay. Map the page copy on write into the address space of the child, and then remap the page copy on write in its own address space. Okay, let me see if when it says remap the page copy on write in its own address space, I guess what that means is disable write permissions on that page in its own address space. Note, the ordering here, i.e. marking a page as cow in the child before marking it in the parent, actually matters. Can you see why? Try to think of a specific case where reversing the order could cause trouble. Okay, I'm not going to do that right now. Do page sets both PTEs so that the page is not writable and to contain PTE cow. Okay, interesting. I might need my full Intel manual document. I'm going to pull that up. Okay. Yo, front forum focus. Yo, what's up? That's both PTE, so the page is not writable, and to contain PTE cow in the available field. So I think this is just an internal data structure of the kernel. It's not, there's no CPU bit or something like this. This is not writable, and to contain PTK in the avail field to distinguish, where's this avail? Okay, I am not seeing that. Okay. Distinguish copyright pages from genuine read-only pages. Right, because we need a way to distinguish this, because we're making these pages appear as if they are read-only. And so when we get a page fault into one of them, we need to distinguish, is this page actually genuinely read-only and it's an error condition if a page fault happens in them, or is the page actually just temporarily masquerading as a read-only page for the sake of copy on write? And it's actually not an error to get a page fault on this page. The exception stack is not remapped this way. You'll need to allocate a fresh page in the child for the exception stack. These docs are here. Sub Dario, thank you for the comment. PTE avail. Yeah, we can take a look into that actually. Where is PTE avail? Ah, right. Okay, interesting. This is cool. I have actually never done this before. I've heard of making use of free bits and page tables or whatever. And I guess this is where it happens. We have all these free bits somewhere. I am thinking it's like right here. There are 3 free bits, and I suppose we can put stuff in them. So yeah, thanks Dario for the hint. What's up, me? Very pleasant form of study. Calm music. It's calm for studies. Wow. Oh, thanks for the compliment. I appreciate that. Okay. So exception stack is not remapped this way. Instead, you need to allocate a fresh page, blah, blah, blah. Okay. Since the page fault handler will be doing the actual copying, and the page fault handler, okay. Okay, since you need to, we'll be doing the actual copying, and the page fault handler runs on the exception stack. So that's just explaining why we cannot cow the exception stack. That is one of the pages we actually do need to upfront copy. Okay. Fork also needs to handle pages that are present but not writable or copy on writes. Which just means read only pages. The parent sets the user page fault entry point for the child to look like its own. Which is just, I believe that's just mutating the internal data structure with the function pointer, I think. The child is now ready to run, so the parent marks it runnable. Each time one of the environments writes a copy on write page that hasn't yet written, it will take a page fault. Here's the control flow for the user page fault handler. The kernel propagates the page fault up call. Which, okay, this is just the function. Page fault up call is that assembly stub we were just talking about earlier in the stream. And this runs in user space. Where was it? Okay. Which calls forks page fault handler. Page fault checks that the fault is a write. Okay, you can check the error code and that the PTE is marked cow. If not, panic. That is interesting. Panic. That's interesting to me because it seems a bit aggressive. Basically, I was expecting that if a write happens, it's basically describing an invalid write. If a write happens to a page that's not a cow page, then we should terminate the process. We don't need to panic the kernel, but I think we're just starting off easy. So we are panicking. Good, okay. Page fault allocates a new page mapped at a temporary location. And copies the contents of the faulting page into it. Then the fault handler maps the new page at the appropriate address. Okay, a new physical page, or well, so we're doing this all in user space, right? So it's just allocating a new page of memory, copies, and then we can map stuff with read and write permissions in place of the old read-only mapping. The user level libfork.c code must consult the environment's page tables for several of the operations above. Like, yeah. Such as for the PTE cow, such as for the PTE check. The kernel maps the environment's page tables at UVPT exactly for this purpose. It uses a clever mapping trick. This is that thing that I think we skipped over a very long time ago. We can read that a little bit later. The kernel maps the environment's page table, that UVT, for exactly this purpose. Lib entry.s sets up UVPT and UVPD. Interesting. Okay, so I don't really get that. I'll just quickly take a look at the mem layout. So this is what it's talking about. Oh, UVPT. It's like 4 megabytes in size. So it's a readable mapping of the page table. Interesting. Okay, so that's a lot of information. I'm just gonna copy and paste it into the board in case we need to reference it later. Okay, time for the exercise. Implement fork do page and page fault in libfork.c. Test your code with the fork tree program, which produce the following messages with interspersed messages. May not appear in this order. Okay, nice. So I don't feel ready to start exactly yet. I think I want to actually understand this a little bit more. So what I want to do is also dumb fork. So this is a sketch of what fork looks like, but it's kind of dumb. It does not do copy on write. It does like upfront copying of every page. So exofork is where we create the blank child. It's a new process, and it's pretty much totally blank. Then we are somehow able to like introspect the address space using some linker symbols and stuff. And then we call dupe page on all of the binary, basically, of the program that's running. But that's not the only thing that's in memory. We also have the stack. And so we explicitly copy that too. But apparently that's the only two things. utext. So we're copying all the way up as far as it needs to go. And then we copy the normal user stack, which we do this in a kind of a clever way. We take the address of a random stack variable, we round it down to the nearest page size, and we assume that that variable is just here. We do not support growing the stack at all. And that code will break. I mean, yeah, nothing, that's totally not supported right now. So we only support these fixed size stacks. Yes. I'm just gonna do a quick check to make sure. I think this Twitter, last time, like, my tweet didn't work. Like, I tweeted and people reacted to it, but then Twitter just like hid it from my profile, and you simply cannot see week 44 on my Twitter profile, which is kind of strange, but it looks like it's doing okay. Also checking Blue Sky. Anyone on Blue Sky? Oh, thanks to Black Gem for the support. Yeah, I'm checking out Blue Sky lately. Okay, so that's how the old fork worked, and this is the key part of it where it duplicates all these pages, and the way it does this is with a few system calls. It allocates a new page. It maps it to a temporary address. It copies it. Okay. Yeah, so do page desktop. So we pass in the environment ID of the child and the virtual address of the page to duplicate into the child, I believe. Exafork returns a PID 0 or the PID of the child, right? So we pass, it's the PID of the child and a page to copy into the child. So we allocate a page at that address in the child because the child is completely blank. And so we can just allocate a page in the child. We can then map it source and source VA to dest. Okay. So source, right. Okay, so and this is where it's a little bit backwards. We allocate a page in the child, and then we map that page into actually our process in the parent, which we can access directly. And so that's why the source is this destination environment and address. The 0 stands for our process ID, and we map it to a temporary location in our process with writable permissions. We can then do a copy. I don't totally know why it's a mem move, but we can copy. It's probably destination is the first one, right? So destination source. So copy from adder in our process into utemp, which is mapped to the child's process, one page. And that effectively fills that page in the child. And then the last thing we do is unmap that from our process, so it only exists in the child now. And that's how this thing works in this OS for this course. So basically, this is the page copying primitive. Okay. Copy only page mappings. And that's the interesting thing. Parent installs page fault. So it's kind of there's two pieces to this. The first piece is the code that actually runs during the fork call, which is the copying, which is like what right here, it's copying all the page tables. Second part is the user space page fault handler, which executes way later in time, whenever in response to memory reads and stuff. Okay. We should map the page copy and write into the address space of the child, and then remap and the order of this matters. Marking the page as copy on write in the child before marking it in the parent. I don't immediately know the answer. It's also time for a 20-second break. So stand up, stretch, get some water, be right back. Okay. Yo, what's up, Wizard? Good stretch. I don't know the answer to that question I just posed, so I will just draw these two boxes to try to help me understand it. So we have these two processes. Maybe I will draw them like this, and I will draw some physical memory over here. I'll draw some physical memory here. Or maybe I will just, copy. So let's say, okay, we should map the page copy and write into the address space of the child. So what we're doing is, okay, so we have the parent, we have the child. Also, I want to make sure my video feed is not like blocking this diagram. All right. So first, step one, map it, copy and write in the child, meaning it's read only. And this will be, let's say it's a writable read write. So this saying first make it here and then make it read only cow. Why is that important? Digitalize, what's up? What's up, y'all? Hope you're doing well. How is your Sunday going? Mine is pretty good. It's very dark. The sun sets in Northern Europe very early in the winter. Okay. So I don't know the answer to this. Kind of bugs me. Map the page, copy and write into the child. And then remap the page, copy and write in its own address space. I'm actually I don't know, a couple versions. So we have this one, it's writable, and then step 2, this becomes read only, copy on write. And then, so this is the high level sequence. We proceed, morning for me, so I still got sun, nice. Step 1, put it there. I am not immediately understanding why this would make any difference, because the child just does not run. It's not like there is some race condition. I mean, when we talk about ordering, like, my guess is there's going to be some notion of a race where, what if something happens at this time, blah, 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 blah. So, like, for example, like, what if the child did run and this was writable? I don't know, let's just map it out, what the other situation would look like. Oops. So if we just simply reverse the order, right, wrong. Except, wait, no, this is, so. So marking a cow in the child before marking it in the parent. So in this case, we mark it, what, like this first? Is this, so yeah. First mark it here, then do both. First mark it here, then marking the page as cow, child. What would be the, so what's the actual opposite here? Is it marking, is it copying the map? Is this true? Is it copying a writable mapping? Oh, okay, I think I'm a bit too slow for this today. So in this situation, the parent has execution. The child is totally frozen. There's no execution going on in the child at all. So I'm thinking, I don't know, the thing that's coming to mind for me is like, what if other threads in the process try to access it? Or maybe it's saying, it's just, maybe it's saying, is it just first the parent maps it cow in itself, and then is there some way that could have problems? I'm not seeing anything right now, because when we're like the program, when we're in the fork, the program isn't like running. It's basically the parent is also paused. So it's not like memory accesses are really occurring to these things. Unless there's other threads, which I don't really know. We don't support threads, and I'm kind of fuzzy on the details of how threads affect fork. Actually, I think when a fork happens, only the calling thread is copied. Maybe. Okay, but anyway, I kind of failed on this one. I'm going to bookmark it for later. Because I was not able to figure it out. Threads is my kind of guess, but so apparently it's important. So the parent can keep doing writes or something, and then we disable that. Yeah, I'm not seeing it. It like maybe would be a problem if the child had a writable page and it started writing to it. Or maybe it's something about if the page fault handler is installed yet or not. Okay, I don't know. Let's just keep moving. Exception stack is just copy. Okay. Okay. Let's just. Okay, I think I understand that well enough. Let's just start coding. Implement fork, do page and page fault and load fork. So, oops. I am going to clear out everything. Get a nice, clean, working slate. Mem layout.c dumfork.c. Okay. Implement fork, do page and page fault. So here we have our user space library that's implementing fork. In the dumb fork thing, it was directly implemented just in the user program, but now we're actually making it kind of a library that can be reused. Set up our page file handler appropriately. Create a child. Hint, use all these things. Remember to fix. So you must allocate. Okay. So I'm wondering about this. All right, so dumbfork does not do any fault alloc. This is the example of, and we need to call this set page fault handler thing. So yes, it seems like this is saying to call this every time fork happens, which seems kind of not optimal, but I don't know. a better place to do that. Yo, hey, John Palmisk. Yeah, nice to see you here, by the way. What made you choose this follow course versus starting with x86 over starting from scratch? A bunch of things. So for one thing, I have kind of a limited time available for doing this, and I suspected I could get going a lot faster if I had an existing skeleton or project infrastructure to get going with, rather than starting with blank files and like blank, just a total blank state, where I would need to invest a lot of time into things just like build scripts and just the basic infrastructure, which is also not really the part I was actually that interested in learning about. So the thing that was pretty attractive about all these courseworks is that they come with these basic skeleton OSs. And x86 does, and it's pretty okay. But I had a lot of complaints about the build system and also the code quality. And in general, the x86 is just way too complete of an operating system to provide the opportunities for me to do the kinds of things I wanted to do. So this JOS operating system in this MIT course actually matched everything I wanted. It has a really nice build system. It has really nice helpers for integrating with QEMU and for debugging. And it also has a nice ultra minimal OS. Like x86 like completely boots into user space and has process support and like does fork and like all this stuff. JOS, when you first start out, doesn't even have user space. It doesn't have any, it has only the most minimal virtual memory possible. And you really do a lot more yourself to build up from that. And so, yeah, if I'm doing this in 2 hours a week, it just seemed like a much more direct way to get at what I wanted. The other major thing is, like with following a course, is like I actually don't know how to write an operating system. And following a course seems like actually the way to fix that, rather than trying to like pure hardcore self-study it. So good question. Thanks for the question. Abhinav, can you make kernel cheats for iOS and Androids? Unfortunately, no, not really. Probably if I invested a bit more into it, but yeah. And what's up, Black Gem? Thanks also for the support on Blue Sky. And your element is easy to understand. Well, thanks for the compliment. Okay, so I'm gonna begin. So is it correct to do this on every fork execution? So we're just going to call set page fault handler page fault. Yeah. Following along, of course, this always felt too much like homework for me. That is true. But to me, this doesn't feel like homework, really. It's like, it actually is really nice. I don't need to design the OS. I just need to implement these functions, which is a long ways away from doing my own OS, but that takes a lot of the work that I kind of don't care about for right now. So I'm just happy to implement these functions. So, so I think we'll be able to copy and paste a good amount here. So, for example, env id sysexo fork. What's up, Afnan? You're not late. I mean, you are a little bit late, but I'm still going for a little bit longer. Thanks for joining. Is it possible to do this on phones? Because I know a few Chinese friends who use kernel cheats and read for games they see is undetectable. Yeah. Yeah, just good material, I guess. Rare to find. Actually, and I think if you look a bit there, like a lot of these like universities just have their coursework online. I'm actually really a big fan of Harvard's CS61 course, which I have not taken, but that looks really awesome. Like, apart from the fact that their webpage actually looks nice and has a CSS, it actually seems like a really high quality course with a lot of stuff. So I think I might have that might have been a good choice for me, but I'm super happy with this one for now. And I'm getting, yeah, like all the learning I care about. Yeah. Okay. So I'm just gonna copy all of this. So we set the handler function, which I don't know if it's correct to do every single fork. Sounds wrong to do a syscall. It is a syscall, I think. Yeah, it's literally a syscall every single time you fork. So then we exo fork. Panic if that didn't succeed. If we're the child, we patch the this end thing and return. And then we get to the part that's different, but I'll just copy the part that's the same. So here's what we return. What is R? Ah, okay. Do I have a stupid... I think I am. I have a... All right, this is done. One. Maybe... Okay, syntactically, you cannot declare the integer inside of this whatever thing. Interesting. And the only purpose of saving it is so we can put it in the panic later. Okay. Cow, fork. Relearn parts of CS anyway after graduation. Yeah, I mean, yeah. That stuff always happens. All right, 20 seconds, quick, stand up and stretch and water, whatever. I'm just also noticing we have a pretty full house today. 21 people in the stream. That's awesome. Thanks for joining, everybody. Okay, so okay. For each writable, okay, so to some extent. Where the parent eagerly copy our entire address space into the child. This is not what you should do. What's up, Nigel? Hello. Map. So how do I do this? So the first basic thing I need to do is be able to loop over all of the pages in the address space and then call dupe page. So I don't know. I am going to copy this and I think void adder. What? Ah, okay, I need to declare this. So to also handle pages that are present. In this case, we just need to map them. Okay. This is actually kind of challenging. I think I need some of these hints. Copy our address space and page fault handler set it. Number 4 sets the user for the child to look like its own. Okay, this is, yeah, actually a little bit challenging. There's a bunch of stuff I am not immediately understanding, like exactly how to do this. But I am just going to focus on this first part for now. And I'm going to try to use every hint they give me. UVPD, UVPT. Okay, remember to fix this. I did that because I copied and pasted it. So I'm just gonna add some comments. So for each page in the process, if it's present and read only, simply remap it read only in the child, no cow. If it's present and write, first map it cow in the child because they said so. Then remap it cow in the parent. Set the user space page fault handler for the child. How? What other information is there? This is the thing Dario said earlier. We use a free bit in the page table entry, apparently. Oh, exception stack. Manual, or like copy alloc a new exception stack for the child up front. Okay. So, yeah, this is kind of how I'm trying to proceed with this. I don't exactly know what to do, but I'm just kind of trying to take what I do know that I need to do and like push it into the code. And then eventually, hopefully I can take each of these things and then go into a bit more detail about how to actually do that. I think this part will be kind of easy, actually. It's via that system call for, we're going to do something like syspage alloc, page map, I believe. So I think this loop is still fairly correct because we're able to use this. We also need to remember the stack. Copy the stack. Well, yeah, the stack is going to be one of those things that pretty much immediately gets cow faulted in, but I guess nonetheless we still need to, we should still copy it rather than full copy it. Copy the stack. So these are roughly the things that we need to do. And something along the lines of here. So we are able to loop over pretty much every page here in the user space memory region that holds the program and the heap or whatever. The stack is a separate area, but it's hard coded. We know where that is. So what we then need to do is then look up the PTE for this page. How? Maybe this UVPT thing they were talking about, which I don't actually know what that is, but they keep mentioning it, so it seems important. And dupe page, which is not implemented. But this is, what is dupe page? Map our virtual page. Into the target env ID at the same address. If page is writable or copy on write. The new mapping must be created, copy and write. Must be. This is that thing that they're asking. Like, we need to mark ours copy and write again. So there's already a few things I don't understand here. So first of all, if the page is writable, that makes sense. If the page is copy on write, how is that possible? Also, what does that even mean for a page to be copy on write? I think what they are meaning here is that the cow bit is set in the page table. So I'm actually gonna come over and copy some of this. Yeah, I think this will be useful to have over on this side of the board. I forget what these things are. But yeah, a page being copy on write means that one of these bits is used. PT cow, let's take a look. It is one of the bits explicitly allocated to user processes. Hex 800. So this is 0 through 7 is 1 byte, and then we have 4 bits, and 8 is the top bit. So we're using this 11th bit in here or something to tag it as copy on write. Yeah, there is probably a good answer for this, but I'm also kind of wondering why we need to keep the bit there. Why can't we store that state separately? And my first guess would be, well, because of performance. But it's good to clarify when things are optimizations. So my understanding is actually putting the bit here is an optimization. We could maybe consider storing it in the struct, like in, actually, I don't know. Yeah, I don't know. Maybe it's kind of stupid to think about it, but you could consider storing it elsewhere, like in the data structure for the process. But it is state that is per page mapping. So it kind of makes sense to put it right next to all the other state that is per page mapping. So, okay, whatever. I'm convinced that it's a good idea to put it there. So I think the key thing, or let's finish reading through this. So the page is copy on write. The new mapping must be created copy on write. Then our mapping must be marked copy on write as. Marking a mapping copy on write means writing that bit as 1 in the page table entry. Why do we need to mark ours as copy on write again if it was already copy on write? I have no idea, actually. That I don't know the answer to this. Something to do with, I don't know, the CPU caching some page table state or something? Yes. All right. What's up, Akash? Are you a professional exploit developer? No. I am a hobbyist kernel developer, kernel hacker. But yeah, more on the developer end of the spectrum. Okay, so I don't know the answer, but I will maybe try to find the answer out later. I'm just going to take it on face value. So maybe this actually handles this mapping. So maybe it's enough to call dupe page like for each, although it says don't do this. But I think it's just referring to this eager copying thing. We are going to have a totally different implementation of dupe page. But dupe page expects something different. It expects a page number. Why? It's the target. So it's a little bit strange, but it's page shift, which is what? Hex 12, yeah. But then we can't. T. So, I mean, I don't know if John Palmisk is still here, but this is kind of also a bit of a downside of doing a course rather than just doing stuff myself. There's a lot of these situations where the course is built a certain way, and I spend a lot of time trying to understand their intentions with this, rather than trying to understand the actual core content of like operating systems development. So like, yeah, and that stuff happens quite a bit. So there are a lot of downsides of following this coursework and stuff, especially doing so while like I'm not taking the course and don't have the support of like TAs and stuff. So here's our loop. But it seems kind of silly because I'm just going to immediately like shift this back. Also, I don't understand why they designed it to have a page number, but maybe there's a reason. Into the target env ID. think it's time to learn about this UVPT thing. Which I think, I mean, entry.s. This is so strange. Because these, I don't really understand. Global symbols ends in C as if they were ordinary global. Okay, whatever. And then UV page directory is at some point some offset from that. Yeah, the blank canvas. Yeah, it does have that downside of like, yeah. Exactly. And like, you can waste a lot of time just doing things on your own, blindly copying random stuff that people can just tell you in the course. And I'm also pretty confident that I've saved time overall. It's not totally clear. I've spent a lot of time debugging random stuff, but the coursework does like give you all these like nice hints. For example, this thing that I don't know the answer to right now. Like if I were doing this by myself, I wouldn't have even known that this was a problem. And I might have spent a lot of time debugging that. Okay, I still don't know what UVPT is. Okay, 20 seconds, stand up and stretch. Okay. So apparently you can include this header file, and I guess, do we do that? No, I don't see that here. Apparently you can actually include memlayout.h from user mode and get access to something. The page directory entry corresponding to the virtual address range. It points to the page directory itself. Thus, the page directory is treated as a page table as well. Love the time for stretching. Yeah, thanks, Black Gem. Just I don't know, just like healthy habits. So I don't understand this, but I'll read it through it. Generally, like, the concept here is the kernel is exposing the page tables to user space read-only, and apparently it's pretty easy or something. John, it's called timeout. It's this like Mac app. It's a page table. I don't quite understand this sentence. But basically what this means, the page directory entry corresponding to here points at the page directory itself. Just to clarify what that actually means. So basically, yeah, here's what the x86, the whole page table thing looks like. There's a single page directory. There's like 1024 of them, I believe. And they each point to a page table. And this whole thing covers the entire 4 GB address range. We, in this OS, have decided that a specific region of memory is going to be special at this, like, it's like a long region of memory too. And it's going to point at the page tables. Sorry. Down here. Plus PT size, which is 4 megabytes. Page table, I believe, covers 4 megabytes. I'll just this over here. Yeah, so this is 100,000 hex is 1 megabyte. So this is 4 megabytes covered by one page table. And this region points to the page directory itself. So it's like one of these things, it's basically as if, like, you have this block. Say we just had like a block, one of these page directory entries that corresponds to the UVPT thing, and it points at here, basically. So you can read the processes page directory by reading from a particular point in virtual memory. And I think that explains actually why they chose to make this an unsigned. Because I think what's going to happen here is we're basically just going to be indexing into these arrays. And this page number is the index we're going to use, actually. So I think I'm starting to understand that a little bit more. But this, like, interface exposed to user space involves indexing into some arrays with page frame numbers and stuff like this. Okay. That's the page directory. What's up, Martin? I have been learning this since February in terms of my streaming, but I've also in general been learning about computers and operating systems for like 10 years. I've just never taken a course in it. And I'm learning quite a lot. There's a lot you cannot learn in 10 years of unstructured learning. I don't know what this A thing is. Okay. One result of treating page directory as a page table is that all PTEs can be accessed through a virtual page table at virtual address UVPT. The page table entry for page number N. Oh, it's worth drawing a diagram. I think I will need to do that. The second consequence that the contents of the current page directory will always be available at UVPT plus UVPT page shift to which it's set to that. Okay, man, this is kind of hardcore. I am confident I can understand this, I just don't yet. I'm gonna copy into this region. I'm gonna mark it as a to-do because I also get the sense that I can be a user of this interface without understanding every single detail. I definitely want to do this at some point. UVPT. It's treated as a page table. Corresponding. Maybe it'll help me to see a bit more. So yeah, this line, okay, never mind. I think it's actually this line takes us very, very, very far back to the beginnings of the course, basically, when we were doing virtual memory setup. And there was this thing that says you don't have to understand. And I'm going to copy it over because now it is becoming relevant. Well, I do sort of understand this line though. This line corresponds to the first sentence here. Oops. It's setting, and I don't know, we can copy this over here. So current page dir is basically an array that corresponds to this page directory. And we're taking UVPT and extracting its index by shifting it to get this particular slot. In this case, this thing that I made a rectangle for. No, I'm just going to drag this over here. Oh, okay. So basically, we're assigning something into this slot, and we're assigning a page directory entry that points at current page dir. Current page dir is used twice here. So this is this like self-pointing. This picture where the entry points back at the data structure is exactly what we are seeing here. So I understand that part. Where I'm starting to fail to understand is like the next sentence and a little bit further. The page directory is treated as a page table as well as a page directory. Is that even possible? So I guess the page directory entry and the page table entry have basically identical layouts, although not really. They are pretty similar, although there are more unused bits of the page directory entry, and page table entries have some extra things, but for a lot of these important things, the layouts are actually identical. And so maybe it's saying that we can actually treat these entries as if they were page table entries. Is that all PTEs can be accessed through a virtual page table. So we set UVPT to this thing. We can see this UVPT. We can see this here. So I've been referencing this memory layout diagram a lot. There's this particular hard-coded address of UVPT. It's actually in kernel space. It's above the top of user space, but it's read-only. It's just, but even though it's in kernel space, it is actually still kind of exported as accessible to user space as read-only. And we can see this entry.s sets the underscore or like lowercase uvpt to this thing, and that is what this is going to resolve to. The thing I actually don't understand is why there's no include, or maybe lib.h already includes it. Yes, it does. Okay, I see. It includes a lot of things. So that's a bit of a violation of like the include what you use principle when you're doing C and C++ programming. So just to make that more clear, I will directly add the include for it because we're going to need it, I think. So when we access this thing, we are accessing this part of memory, which points to the page directory. But actually, okay, so one thing was kind of wrong at what I showed. So when we were looking at this code snippet, I was showing at how there is, this is actually in the kernel's page directory, which is not what we are looking at or dealing with right now. We are dealing with a user space processes page directory, which is distinct from like the core kernel's page directory. And that's actually this thing that I skipped over. This is the exact same thing, but for the user space process. And this is the one that's relevant to us. So this env pagedir is the actual thing we're going to be kind of looking into. And so when we use this lower case uvpt variable, it is assigned to this capital uvpt macro, which is a particular address in memory. So we're accessing this memory. This line of the kernel setup code makes, it causes accesses here to get mapped to point at this data, at this env pagedir thing in kernel memory. I'm just going to keep drawing this out. So we have the process. We're going to draw the arbitrary line. This is the top of user space, and then the kernel mem is here. We have this uvpt region. We also have, for example, the env pagedir, which is the page directory for, that's this thing. It's this block that lives here. And the mapping is such that basically it also appears here because this memory is mapped to, how do I, is mapped to right here. So basically, so this thing, not accessible to user space. Accessible to user space. So this is kind of what we're seeing. We can read memory here, and actually it's kind of forwarded along, and we have and forwarded over to here, which is actually where the page directory is stored. But it's a read-only alias, basically. So I understand that, but I kind of, what do you do with that? It's like, okay, you can read page directory entries. I'm kind of still wondering like what the so what of that is. Because I can understand that we can now access all these page directory entries by reading memory, but what we actually need to do is read the page table entries, which are these things over here. Like we can read all these things, but I want to be reading these things. And there's, I don't know, there's some way to follow the pointer or something, but I don't quite see it yet. But it's claiming that one result of doing this mapping is that all PTEs can be accessed through a virtual page table. The PTE for page number n. And this is the key thing I don't understand. The PTE for page number n is stored at UVPT n. And I don't understand that because I would have thought the page directory entry for, I don't know, like the page, yeah, for like the page table, the page directory entry is stored at index n, but it's saying the page table. Wow. So this is actually yeah. Yeah, I already can tell I have a serious misunderstanding because I also don't understand this second part. All right, 20-second break. Stand up and stretch. Yeah, I can already tell I have a serious misunderstanding of this. It's saying a second consequence is that the contents of the current page directory will always be available at this virtual address, but that went against my understanding. My understanding was that the current page directory lives at UVPT, but that is clearly not the case. It lives like strangely a bunch higher. Page directories. Okay, but I think, okay, but I'm kind of starting to get it. I think there's some kind of implicit dereference going on that I wasn't quite seeing. But I'm starting to understand this whole idea of how, okay. Under normal circumstances, a page directory entry points to a page table, period. The page table has page table entries. I'm now understanding what it meant. In this exceptional case, we are pointing this thing not at a separate page table with page table entries. We are pointing it at itself, and therefore this block of memory gets interpreted like both as a page directory entry, But when you start to access the memory addresses in this range, that's kind of, okay, I mean, we can step through that to actually understand that. So under normal circumstances, you access some part of memory. It belongs to one of these blocks, one of these page directory entries. The CPU goes and finds it, and then it walks it and finds the next corresponding one. And then that is used to resolve this thing. That's the normal case. What's happening now is this thing. So we access a address within this region, this special region, the UVPT region. First step, so we access the memory. This thing is located. We then do the next walk. Instead of going over here, we point back at ourselves. And then this is like a bit of like the brain bending thing that I'm not understanding. So then we then do another access. I feel like it would be nice to have an example of a concrete like memory address to walk through this example with and divide up the bits and stuff. But okay, I'm getting a bit closer now. There's like a certain kind of magic that happens when you point this thing back at itself. Maybe it's helpful to just use this thing to take this into account. So step one, when you try to access okay, let me make some more space. This is the thing. I mean, this is like kind of basics, but I am just needing a bit of a refresher here. Yeah. So just collecting all the relevant information. So we have an address. The first 10 bits, or I guess the highest 10 bits, page directory index, page table index, offset. So we access what I kind of want to just do is just quickly enter a debugging session. Emu GDB. Okay. I just want to see what the actual value of UVPT is. Oh wait, no, it's right here. Okay. Yeah, it would be nice to have this like parsed somehow into the bits. But whatever. That's what our Python interpreter is for. Is that visible on screen? Okay. Here's the part where I wish I had these handy things here. Right. So we shifted down 22. we get something. And then the PTX adder shifted down 12 and hex 3FF. Right. That makes sense that it's 0 because we're completely aligned on a page table. Zeros. So maybe that wasn't that helpful, but it's a concrete example of an address that we can use to work through this. So what happens? So step 1, we're going to, I'm just going to copy this over here. So step 1, we're going to dereference this pointer. The pointer is within our special range. The pointer is within the special range. Step 1, we compute the page directory index based off of this, and it's hex 3BD. And so we go up in here, and we're going to find, let me copy and paste the right, this thing. This is actually the one we want. So we're going to go up here, and we're going to find this page directory entry, which points at the end page dir as present user space accessible but not writable. Then it is time to, so we found a valid entry here. So that's step 1. Now it's time to walk the page table. So we're going to follow the arrow to this next thing. And rather than doing the normal thing of going over here, we point back at ourselves. And then what happens? So the normal step 2 of all of this stuff is you then take the PTX number and you index into this table to to get a page table entry. And okay, under normal circumstances, you do that, you check it to make sure it's present and stuff, and then that points to the place in physical in memory, wait a sec, where you're going to access. So in this case, we point back to ourselves. We use the PTX to index into the page table yet again, treating it like a page table, which is what it's saying. The page directory is treated as a page table. And in this case, we are going to like access the bottom one or something. Which I have no idea what's there. That because we have PTX 0. And that's the part where I kind of don't understand this. I have no idea if is the bottom page mapped? We can tell based off of the memory layout. In our case, 0 should not have anything mapped. So I am not really understanding how this works then, because it would be as if there is an invalid page table. Ah, and that would fail. So yeah, so maybe that's totally right. Oh wait, no, I think I see it now. This is like sort of blasting my brain a little bit, but it's based like, let me see if I can explain. I'm like sort of getting the intuition behind it. Okay. Under normal circumstances, we walk these tables and take this offset field and like bump this thing up and access this spot. I think the general intuition behind this is that bump is going to occur on the page table and allow us to, and actually rather than pointing at memory, it points to a page table entry. And so I'm going to clear a bit of this out. I don't know. I'm going to draw a bad diagram. But this is normal, the normal world. We're now living in a bit of a weird world. This arrow is kind of in the way. Okay. Page directory entry. We're now living in a weird world where this thing where it kind of looks like this actually. And this is actually really clever. Wow. I think I'm kind of getting it. So under normal circumstances, you like walk once, twice, get a thing, and then bump it up. Under this world, we're kind of doing the exact same thing. You walk once, twice, get a thing, and like bump up to a specific place based off of the offset. And rather than that final destination thing being a physical address, it is the pointer to a page table entry. I think I must be losing absolutely everybody because like I'm barely understanding this, but I think this is the general concept of how the technique works. And have you done any ARM OS dev or embedded stuff? x86 first one looks so much more complicated. No, actually. Yeah. I am not sure ARM is less complicated. I think all of these concepts that we are dealing with apply to any virtual memory implementation. The reason x86 can be more complicated than ARM is because x86 has a lot of legacy features like segmentation and stuff like this. I don't know if I have stuff like that in my map. Yeah, so x86 has a lot of legacy features like memory segmentation, which do make things complicated, but at this point we have completely disabled all of that stuff. And so we're now just kind of working with like the more modern virtual memory world. And I think all of these concepts apply also to ARM. And so I think actually this technique would work with ARM. Okay, so I think I've tried to visualize this topic a little bit more, rather than doing the normal world where we bump, and then point to a page of memory, and then go up to get some data. We find it, bump again back to ourselves, and then dereference that to point to a page table. Because we can apparently we can interpret a page directory entry, like it looks close enough to a page table entry where this works, because we take the page, under normal circumstances, the CPU takes the page directory, checks the permission, the bit or whatever, and then uses these bits to find the next table. And then CPU goes to this entry, checks some bits, and uses those bits to find the next thing, which in the normal case is a page of physical memory. And here, when we're doing this, we are it's almost like we're doing like a little bit of like a type confusion thing with the CPU. We are actually passing it some data that's not actually a page table entry. It's expecting a page table entry, which looks like this thing below here. We are like secretly passing it a page directory entry, which is not the same thing, but it's close enough. I think that's the main point here. When the CPU takes a page table entry, it is going to expect a couple of things. It's going to expect a permission bit over here, some read-write bits, and some other bits for doing its walking and its checking. And then it's going to expect an address field in the high bits. And I'm going to kill the palm tree because I'm kind of in flow, and I also need to go in the next 15 to 20 minutes. But yeah, those are the most important bits that the CPU cares about. The permissions bits for doing the checks, and then this address portion for finding the next thing. The page directory entry is different from the page table entry, but not in any of the places where it matters. In the places where it matters, the permission bit, the read-write bit, user supervisor, whatever, I don't know these other things are, but like in these three low bits, those are the same, and also in this high bit chunk. So it's the same in all of the places it matters, which apparently allows one to reuse this thing as a page table entry and do this kind of weird thing. So I think I'm kind of starting to understand it now. Catching up on the chat. Raj, I understand 30%, but I love your stream, bro. Thanks so much. Really appreciate that, Raj. I know it's like this stuff is like kind of crazy. I don't really think anyone should this type of, yeah, I don't think anyone would should really expect to fully understand this unless you were like a real like absolute expert in this stuff, because like I can only understand this because I've been doing the stream for like a year. So like don't feel bad or anything if you don't understand it. If you do the course like I have, you will be in a better spot to do that. But yeah, the specific type confusion thing is profoundly cursed and not something I've had to do with ARM virtual memory. Yes, so this type confusion thing is not something you have to do, I think. I would call this a hack or a clever technique or a trick, but I've never heard of this, and I would call this like kind of a hack if you feel like exposing the page tables to like user space. Maybe it's like, which is kind of a weird thing to do. If you are doing normal kernel development, you are almost certainly not directly exposing the page tables of the process to user space, which is why you probably haven't run into this. But for whatever reason, the course is doing this because we are implementing copy on write fork entirely in user space, which requires user space to have access to the page tables. But if you are not doing user space, like so much stuff in user space, you don't need this, because when you're within the kernel, you can just access the page tables like easily. Like you can just dereference any of the memory that's relevant. But in this case, we're trying to access it all from user space. And we're trying to do this in a way where we don't simply allow user space read access to all of kernel memory. I think that's the more concise way to put this. This is kind of a clever hack to expose the page tables of a process to user space while minimizing the amount of actual memory, like pages you need to make readable to user space. So in this case, we were able to expose, I believe, the entirety of the page, of the valid page tables to user space while only offering a mapping of 4 megabytes, I believe. But I agree, it's like weird, cursed. I find it very interesting, but I would consider this a bit of an abuse of the page tables. And I think that's awesome. I am super glad to have learned about this technique. And that is probably not something I would have learned if I were doing this on my own. The Intel environment makes the ARM manual look easy. I'm glad I never did x86. Oh, really? Interesting. I've never done, I'm curious what these ARM things look like. I've looked at the ARM manuals just for the instruction documentation, but I've never looked at the page table definitions before. Okay, so that, yeah, sick, CCC, yeah, awesome. So let's maybe walk through this a bit more. I think the thing that I was not understanding, which is also not documented, is that you cannot actually access every index of this array. If you access memory that's not mapped, it will like crash or like segfault or whatever. So it's only safe to access elements of the array that you know are mapped. And the reason is because, let's walk through this example again. This is the address of UVPT. It's at the bottom of this mapping. And I kind of assumed we would be able to access it. But as I was seeing and showing earlier, if we take the first step, we take 3xbd and index into this table at 3xbd. We get the UVPT page directory, which points to the bottom of this thing. We'll just visualize it like this. We then take the second index, PTX, and index into this. It's 0, so we index into the 0th element of this array. In this case, that is not going to be valid because in our memory layout, we do not map anything at 0. So we are not going to have a valid page table entry here at 0. And specifically, it is not going to have a valid present bit. It's going to be 0 here. The CPU is going to come along and try to interpret this page directory entry as a page table entry. So it's going to do its permissions checks, for example. And it's going to look at this data. It's going to look at this one and it's gonna be like, or this bit, and be like, okay, I see a 0 here. This is an invalid memory access, and it's going to cause a page fault exception or whatever. And that's why it's not going to work to access this UVPT thing at index 0, which maybe that was like obvious or something. It wasn't completely clear to me that there's a lot of restrictions on exactly what you can try to access with this. Let's do an example of something that actually should work. And what would be a good example of this? Maybe let's like literally anything else, or like let's just let's come back here quickly. So you map, so we take a virtual page number, right? So let's just take the stack as a really simple example. U stack top. But why did I make that a string? Let's just make that a really simple example. Let's say we wanted to use this UVPT thing, this UVPT mechanism, UVPD mechanism, and use it to find out information about the stack's memory permissions. Actually, the U stack top is not what we want. We actually want the bottom of the stack, which will actually be mapped. So U stack, and we'll assign that to this. Let's do exactly the same thing we did above. I kind of wish I had made a function, but whatever. I'm gonna call this UPDX. And then we'll take U stack and we'll call this UPTX. Okay, that's a bit more interesting. And then the last thing we will do is we'll take the offset, which is U stack, like, and I don't know, hex 3FF, I think. U LA and FFF. Oops. So now we get the offset, which is 0, which makes sense because this is aligned on the bottom of a page. So I'm going to copy this in here. So now let's work through this example. I actually think I'm missing one thing. So in order to use this, we need to shift it. So this is the PN. So this is the page number of the U stack. So now let's walk through actually trying to use this thing. So one of the things our fork in user space is going to need to do is it is going to need to cow copy the stack, which is a little bit silly because the stack is going to be completely just written to immediately by the child. But let's just for the sake of example, like we still do want to do this. So let's cow copy the stack. And to do that, so the way this works is you pass in So what we've seen in the code here, you pass in the PN, right? The PN is page number, and you use this to index into these arrays. So let's try doing that. It's kind of interesting. So I'm still kind of working through my understanding, but actually so that's going to result in something that looks like uvpt at ustack 12, which is uvpt at hex EEBFD, I guess, right? PTE for page, right? PTE for page number N. This is our page number. And the question is, so what address does this produce actually? I think it's, the way we compute this is we take the base of uvpt, we're going to add something to it. It's going to be this number times the size of ptet, which is 4 bytes. So we'll do 4 times this thing, and we get a number, which is super interesting. Oh, I see. Okay, so then now, oh man, now, okay, pdx x return, wow, okay. I'm just going to finally make some functions for myself, even though I'm going to only use them once. ptx return oops, def offset x return x and hex f. Okay. So now we have this super interesting address, which is UVP. It's like UVPT accessed at ustack. I'm just going to call it like this. And PDPT ustack. So the PDX, the PTX, and the offset. And so now, so we've gone from what our call site in the code will look like. We've converted that into what the actual kind of C array access that's going to happen. We've converted that into the actual address that's going to be processed by the CPU. It's this virtual memory address. It's kind of weird looking. And we'll see if I know what I'm talking about. And so then we've taken that address and we've parsed out the bits according to how the CPU is going to process it. And so the first thing that's going to happen is when the CPU tries to access this address, which is in kernel space, first thing, take the lower bits for the page directory index and index into the page directory. So 3BD will always hit this UVPT thing because we are in that region, just like over here, 3BD. Next up, so instead of accessing 0, like we did in our example, which didn't work, we are going to apparently access something else. 3BA, which is going to be some other entry. And let me go back to the memory layout. I think I'm kind of close to understanding this. What is a little bit confusing? Okay, my brain is a little bit getting fried. But yeah, so 3BA is going to point at another page directory entry. It's actually pretty close to UVPT, which I don't know, is that right? It's 3BA, which is just like 3 or so. Like 3 or so below D, which kind of doesn't make sense to me, but maybe it's right. So 1, 2, okay, 1, 2, 3, 4. So I don't exactly know. I mean, it shouldn't be that hard to take one of these indexes and resolve it to the virtual address that range that it covers. It's actually pretty easy, probably. It's just the number times 4 megabytes, I guess. So just curious, actually. So we do this times. Is this going to be the UVPT? Yes, EF4, which is what we see here. So if I wonder what happens if I just do the same thing, EBA, which yields EE8. Okay, it's not, okay, I think I actually did something wrong, but just for the sake of, yeah, so this is actually, I think I did something wrong here, maybe, or maybe here? I kind of thought PTET, am I wrong about how big a PTET? I cannot, no way. PTET is 4 bytes. EEBDF. Oh, did I mistype? BF, did I miss that? Wait a sec. No way. UStack. UStack BFD, right? Stack BFD. BFD. BFD 1000. Okay, so I'm pretty confident, unless but this is the thing that matters most. Ustack shifted over, is it 12? Page shift, right? Page shift 12, right? Shifted over 12. Because wait a sec. Yeah, it's shifted over these 12 bits, right? So she's not shifted over 12 gives us the PEEBFD. This plus 4 times hex EEBFD, which I am pretty confident somehow. Is that how C array access works? You take the thing times the size of the type, which is 4. So I'm somewhat confident it's this 7F BAFF4 thing. Did I make a mistake here? PDX, you shifted over 22. Yeah, shifted over 22. So these are the macros that they wrote, these are the macros that I wrote. And I skipped something, but I don't think it should matter. We're shifting over everything over, like, shifting over 22. Yeah, that should work. Shift over 22. Oops. Then, oh, sorry. 12 mask 3FF and then hex FFF. So I think that should all work, right? So what is going on? EF7 BAFF4. And we do all this stuff. Okay, I don't know. Yeah, I might not have enough time to fully dig to the deep reason there. But even if it is slight, or I don't know, maybe I didn't follow it through quite enough. But, so yeah, first step, we receive this arbitrary thing, we unpack it as the CPU. First one, we index into page directory, we get the UVPT. That's totally expected. We then take the second thing, 3BA. And index into theirs somehow. And get whatever's there, this 3BA thing. Which is what? So 3BA contains the mappings for the EE8 region, the whole EE8 region of memory. It's EE8 plus 4 megabytes, which, where does that get us to? It's EE8 all the way up to what, like EEC or something? Actually, wait, okay, yeah, that makes sense, because our stack resides within this 4 megabyte region. That actually does make sense. Okay. And so our stack is like some offset within the 4 megabyte region that is kind of like governed by the page directory entry at hex 3BA. That actually does make sense. Okay, so we go there into here and we find the page directory entry that corresponds to, it's sort of just like this chunk. Can you see my screenshot highlighted? Like this chunk, roughly. I mean, actually, no, not at all, but it's like somehow like this-ish chunk of 4 megabytes. And okay. Because we have things that are actually mapped into that 4 megabyte chunk, that page directory entry is guaranteed to be valid. And it's going to have a page table that it points to. And so in this case, I'm just going to draw like make this white. It's the for 8. What is it? EE 800,000 to hex E. I'll make this a little bit bigger. Hex EE C 100,000. And like importantly, the address we're trying to access is in there. It's this EEBFD thing, which is within this region. So actually, I think this will be kind of cool. So move this away. Actually, what is going to kind of happen is the way the page tables look, there's some page table entry in here that points to this thing, right? That's how it normally works. There's a page directory entry in the normal situation with the 3 levels. Page you access to try to access the stack, you give it a stack address. It parses out the PDE for this general 4 megabyte region that we're in. It's like this, there's like a 4 megabyte region that this is sitting in. We go and then one level deeper and find the page table entry that points directly to this page. But in our world that we're doing this right now, the page table walk like ends like here. It's 3 levels deep. So this is like a little bit, I don't know, I wish I could make it more, lower the opacity. But what's actually happening here is, I'm just gonna cover it up. So we then locate the 3BA page directory entry, which is this one, and it points to, and that's gonna point to this page table that includes an entry that points to the stack. But then we only have one more step of the walk to do, and that is to actually add, we're going to dereference the pointer in this page directory entry that points to this page table. That's going to be valid. We're going to, as the last step here, add the hex FF4 offset to the base address there. Basically, it's hex FF4 between these two things. And it's going to point at somewhere in physical memory, I suppose. I think all of these addresses are all physical addresses. And so it points at the physical address where this page table entry lives. And that is what we're going to read. That's what user space is literally, it's going to dereference this thing, and the CPU is going to give back this PTE. Yeah. Wow. So that is how that works. What's up, Space Pakal? That is how that works. That is wild. I spent the entire stream understanding this very interesting hack, abuse of the x86 page tables. Wow. And I need to go. I'm out of time. Very much out of time. But next week we will continue. Now that I actually understand this, we are now in a spot to actually do this like copy and write fork thing with like all this stuff or whatever, and actually write a bunch of code. We're going to need to use these arrays here in do page to query the page tables effectively. If we were in kernel mode, we would simply be able to use all these kernel mode functions like page lookup, for example, is like one of these classic kernel mode functions we've been using all over the place to query the page tables and get information about them. But the key thing to remember is that we are doing all this from user space. Now we're doing all of this within user space. We don't have access to this function or anything like that. So we need to use this separate like mechanism, which is really insanely hard to understand, melts your brain to understand it. At least it did that for me. I still don't really get this last one, but I kind of do get it. And so this is the mechanism which allows user space to query the page tables in lieu of directly calling all these kernel functions and having just like read access to like all of kernel memory. All right. Digitalize now, set up nicely for next week. Yeah, thank you for watching and hanging out. This was a weird stream. This is just like zero coding, lots of brain melting sort of stuff. But yeah, pretty interesting technique. Never heard of this before. And I would call this some pretty like elite stuff. Wow. All right, that's it for me. I gotta go. I'm gonna end the stream here. I'll do my normal plugging of myself. Have a Discord. Feel free to join. Let me get the link. Feel free to join the link. Please subscribe to my channel if you like what I'm doing. Feel free to leave a comment or like or whatever. And that's it. I do this every week, and I'll see you next week. Have a nice one. Bye. Bit operation, nice. Cool.